Let's say I have a piece of rod, and this piece of rod is pivoted. It means like there is a hinge there that you can rotate about. It's pivoted at this point, say P, and suppose that there is a force that is pulling it. Right, let's say in this direction, there's a force pulling it in this direction. Now we can imagine that this force would then cause the rod to rotate about the point P, and we think of it as a turning effect. The stronger the force is, the bigger is the effect, and the further the force is from the pivot, the stronger the turning effect. Also, the moment is a quantity to tell us the strength of this turning effect, and it's defined in this way. The moment is equal to force is equal to the force times, now this part is important, times the perpendicular distance from the pivot, to, now this part is the most important, to the line of action of the force. Now I cannot emphasize how important this part is, the line of action of the force, meaning the distance that we are talking about here, this distance, the distance, okay, it is not the distance from the pivot to the point where the force is acting, right, where the force is pulling. It is not that distance. All right, the distance is the distance from pivot to the line of action. Now, what do we mean by the line of action? It means, if you go to the force, the position of the force, we imagine drawing a line along that force through the point where it acts. All right, a line in the same direction over the force. That is the line of action, right? This is the line of action of the force. And a perpendicular distance means we go to the pivot and we draw a line to the line of action of the force, a line that is at 90 degrees to this line of action. And this is the distance. This, if I call this D, from there to there, that's the D. So it's rather it's a little bit more complicated than just a distance from pivot to the point where the force is pulling at. Okay, so we have to remember this, right? This is the correct distance. So that's moment. In the special case where this angle is 90 degrees, that means if the force is just pulling, say in this example, directly downwards, then the distance D would happen to be the same as this distance, right? Be the same as this distance, but not in as I draw it when the force is acting at an angle. Okay, and that's I want to talk about how we can use this moment to calculate forces especially when we talk about a couple where we have two forces rotating a body. Okay. So suppose now that I have a piece of rod again. So that's my piece of rod. Okay. Now suppose that I have a force, one force pulling my rod this way and one force pulling my rod that way. Let's say the two forces are parallel, opposite and equal in magnitude. Let's say this force is 2 newtons, this is 2 newtons, and let's say okay, let's say the distance between them is, say, 0.4 meters. So we have seen earlier that we can find the torque of what we call the torque of this couple, which is the same as the turning effect. The torque, right? The torque of this couple meaning the pair of the two equal opposite forces that are not along the same line, so that can create a turning effect. The torque of this couple is the magnitude of each force, which is the 2 newtons, times the perpendicular distance between the two lines of the force, 0.4. So the answer is, in this case, 0.8 Newton meter. That's the torque of the couple. Now, I've described the torque as a turning effect of the couple, and only just now I've talked about moments as the turning effect of a force about a pivot. So both are turning effects. Is there some connection? There is indeed. Let's look at these two forces, and let's think about finding the moments of the two forces. Now, if you remember, when I define and describe moment, I have to talk about a pivot. So I talk about a point about which the force rotates the object. Now, but in this case, what if I don't have a pivot? Well, actually, when we talk about pivot when calculating moment, pivot doesn't have to be a real point where you actually attach the thing. It can be any imaginary point. So, for example, I can just say I can just think of a point, maybe here at one end of the ruler, okay, and imagine that that's a pivot, and that's fine. Okay, it just means that maybe if I choose a different pivot, then the moments from the forces could be different. Okay, since distances are different. So in this case, let me just pick one pivot. Now, what I'm going to say is that if I have a couple, all right, if I have two opposite forces like that, then the total moment is actually the same wherever I choose the pivot, and this is what I'm going to show. Okay, now I need some distances. So let's say this distance here is, let's say this distance is 0.2 meter, and now I want to find the total moments of these two forces about this pivot. I'll call that P1. Now let's see if the total moment is indeed the same as this torque of the couple. So here goes. Right. The total moment. total moments is equal to. Let's think about the two forces. This force here, if we have this in imaginary pivot down here, this force here would tend to rotate the object, the rod, this way, right? This way around the pivot. So that would be clockwise. All right, that force would tend to rotate anti-clockwise about the pivot. So the moment from this force about the pivot is 2 times 0.2. In this case, this angle is already perpendicular. Okay, so that's the correct distance. So 2 times 0.2. 2 times 0.2. Now, the other force, this one, tends to rotate anti-clockwise. Its moment will be 2 times distance here is 0.4 plus 0.2. So right down here, 2 times 0.6. Okay. Now, but before we add them, we have to be careful of one thing. Now, moments, like forces, have directions, except that the direction is not a simple straight line direction like just a force. In this case, the direction is that this force would have a clockwise direction, and the other force would have an anti-clockwise direction. So, like when we solve problems for motion along a straight line, we have to choose a direction to be positive to make things easy. Now, and let's see, we did that when we do motion along a straight line. Now, in this case, we do that when we have forces in 2 dimensions. All right, if you start having forces pointing out in all and everywhere in all 3 dimensions, then things gets more complicated and we need to use vectors, so we shan't go into that for now. So the 2 forces, right, I want to decide now whether I should choose the clockwise or anti-clockwise as the positive. So now let me write this down just so as to be very clear. I am going to choose the clockwise. Like motion in a straight line, it doesn't matter which direction you choose to be positive, as long as you stick to it in your calculations. So I'm going to choose clockwise to be the positive direction. Okay. Positive direction. So anti-clockwise will be negative. And coming back to the moment, my 2 times 0.2 came from this force, which tends to rotate clockwise. So I should give this a positive sign. And my 2 times 0.6 is this one, which tends to rotate anti-clockwise. Okay, so I should give this a minus sign. So now I have my signs. I can now add them. Okay, so that's 0.4, that's minus 0.12, minus 1.12. So the answer is minus 0.8. And moment is force, has units of force times distance, so that would be Newton meter, just like the torque. Newton meter. Minus 0.8 Newton meter. So the moment, the total moment, is a turning effect in the minus direction, which means in the anti-clockwise direction, right? As we would expect of these 2 forces. Right, now I'd like you to take a look at something. Take a look at this number 0.8 that I calculated by adding up the moments, and take a look at this 0.8, this number, which I got from using the formula for the couple, right? The formula of force times perpendicular distance. They are the same, right? Both are the same, right? There's the minus sign here, and that gives us the additional information that it is anti-clockwise. All right, but the magnitude, as you can see, is the same. And in fact, in the torque of the couple, once I've defined the that clockwise is plus, okay, to be very precise, I really should add in a sign as well, because this torque is anti-clockwise. Okay, so where are we now? So okay, so let's review what I've done. How did I get this point 8? Right, I added up the moment, but before I added up the moment, I had to do something. I had to decide on a place for my pivot, because I need a pivot to find the moment. And how did I decide that the place for the pivot? I just picked one point at random. That's all I did. Okay, and if I just pick one point at random and I can get the same answer, does that mean that if I pick another point at random, I can also get the same answer? Indeed, we can. So let's try that. All right, let's try that. Let me pick another point. Let me pick say this point, right? I'm going to pick something drastic. I'm going to pick a point right at one of the forces. Okay, right, so maybe it'll go wrong. Okay, here we go again. Let's try this. So if I want to find the total moment about this new pivot, which I call P2, okay, let's say this is a total moment. So another thing about finding moment is that we really need to specify the pivot, because obviously it's going to be different. Distances are going to be different if you have a different pivot. So just to be very precise, I'm going back to this calculation, and I'm just going to add in this detail. Is a total moment about the pivot P1. Okay, so this time I'm going to do it about the pivot P2. So okay, find some space here. Total moment about P2. Let's try and find that. What would that be? Right. So about P2, let's look at the two forces again. This force, this 2 Newton force, which is right at the pivot P2. What is its moments about P2? Okay, we know moment is force times perpendicular distance from pivot to the line of action of the force. So what is that distance in this case? Distance from this point to the line of action of this force, but this point lies on the line. So that means that the distance is 0 in this case. So we have a force times 0. So that's my moments. Okay, that's my moments here, 0 for this force. What about that force? Okay. That force is 2 times 0.4. Right, 0.4 is the perpendicular distance between the pivot and the line of action of this force. So 2 times 0.4. 2 times 0.4. And the sign, right, this force has an anti-clockwise turning effect. Now since we have decided to choose clockwise to be plus, anti-clockwise should be negative. So I need to put a minus sign here. So 0 minus 2 times 0.4 is the total moment about P2. Now compare 2 times 0.4, which is 0.8, okay, with the torque of the couple again. They are the same, okay, and compare this 2 times 0.4 with the total moment about P1, about a different pivot, and they are the same. So we have a very important and useful result. Okay, now if you take the total moment about any point as the pivot, whether it's P1 or P2 or just pick any other point, you will get the same answer. Okay, but there is a condition. Okay, there's a condition. Obviously, if you have just one single force, that's not going to work, because if you have just one force and you pick a pivot at a different point, the distance will be different and your answer must be different. Now the condition here for this to work is that the resultant of the two forces, must be 0, so that we only have a couple.